magnetic field lines. What are magnetic field lines means? I can write that as this is nothing but the imaginary path. The imaginary path in which a free unit north pole, free unit north pole would tend to move, in magnetic field, magnetic field is known as we can say it is called as simply magnetic field lines. So magnetic field lines is nothing but what we told imaginary path. It is an imaginary path in which a free unit north pole who tends to move when placed in magnetic field. The magnetic field. In which direction it is moving when placed in the magnetic field? That is the direction in which it is moving. There, if you draw imaginary path, that imaginary path is called as magnetic field lines. To analyze that one, I will take one example. This is a bar magnet. I am taking here north pole, south pole. Suppose here, if I leave a unit north pole here. So this is a unit north pole. If I leave unit north pole, what will happen? North repulse. And this north also will attract toward the south. So this unit north pole will be moving towards what? South pole, like this. So this unit north pole is moving towards the south pole. Unit north pole is moving towards the south pole. Observe carefully the direction. Here north repulse. This is a M naught. Let me write it as M naught. M naught means generally I denote M naught as what? M naught I will be denoting with as a unit north pole. This is M naught. So this unit north pole is traveling toward the south because the north pole attracts toward the south pole. So when I left near north pole, automatically it's going toward the south pole. So the direction in which it is moving, in that direction, if I draw one imaginary line, that line is called as the magnetic field line. That line is called as magnetic field line. Magnetic field line means what we told now. You observe here, it's an imaginary path in which a free unit north pole. This is a free unit north pole. M naught is free unit north pole. When left here, automatically it is moving towards south. Why? This is not. This is a U north pole. North repulse. North also attract towards south. So the path in which it is traveling towards south, then that path, if I draw one imaginary line, that line is called as magnetic field line. That line is called magnetic field line. I hope you understood what is magnetic field line. Let us see its characteristics here. Suppose, generally, monopoles does not exist in nature. But now I am taking here, monopole does not exist in nature. I am taking only north pole. This is isolated north pole. Isolated north pole I have taken. So how the direction of the magnetic field lines to here means? Generally what we have to do, we have to imagine unit north pole here. So if you imagine unit north pole is north already, this is north inside. North repulse. Here if I leave unit north pole, it repel like that. If I leave unit north pole, repel like that. Wherever I am leaving the unit north pole, it repels away, that is radially outward. The magnetic field lines, how they are? Radially outward. So the field lines are drawn radially outward. Now you can clearly observe here what is the direction of magnetic field lines means. Simply radially outward field. Radially outward. Field is radially outward for unit north pole imagination. If you take unit isolated south pole, just now previous isolated north pole, now Isolated South Pole. Isolated South Pole I am taking means what is the direction of field lines? The direction of field lines are here I imagine unit North Pole here. North will attract towards south. So all the field direction are towards south. So whenever we are discussing the magnetic field lines, the magnetic field lines are towards the south pole and away from the north pole. So here we'll write what is the direction of magnetic field lines towards south means radially inward. Radially inward. That means I can write magnetic field lines are towards south pole and away from north pole. This is a discussion made for isolated North Pole, isolated North Pole, isolated South Pole, only North Pole and only South Pole. Magnetic field directions are like that. Now, suppose here in next page, I am bringing one North Pole and South Pole close to each other. North Pole and South Pole close to each other. So what will happen? Magnetic lines of force directed from north to south. Already we told north to south. North to south, the magnetic field lines are directed here. Now in the magnet, if you observe, inside the bar magnet, north and south here, the magnetic field lines already we gave this information directed from north to south. Directed from where to where? North to south here. So here, north to south. And this is the direction of magnetic field lines. They are always directing from where to where? North to south, outside the magnet, outside the magnet. Inside the magnet, they are directed from south to north. Inside from south to north, outside from north to south. The magnetic field lines. Here, magnetic field lines are forming closed loops. Magnetic field lines are forming closed loops. This is the major difference for electric field lines and magnetic field lines. Magnetic field lines forms closed loops. Electric field, their electric field lines are there. They are open loops. In that chapter, we got that information. Now coming to magnetic field lines, they are directed outside from where to where? North pole to south pole. Inside from where to where? South pole to north pole. Like that, magnetic field directions we can give in a bar magnet. Suppose now here uniform magnetic field. How to represent uniform magnetic field means the straight and parallel lines will give us uniform magnetic field indication. So magnetic field is uniform. Uniform means everywhere strength is same. So we have to draw by drawing parallel lines. Here, if you leave one pole here, so suppose this pole is what type of pole? Let me take this is north pole. If I leave north pole of pole strength M, what will happen? Remember, always magnetic field lines are directed from where to where we told? North to south. Magnetic lines, field lines are directed from north to south. So I have drawn uniform magnetic field lines like that. That means the magnetic field lines are directed from where to where? North to south. It is uniform field. Uniform field indicated by straight and parallel lines. Straight and parallel. Equal magnet. This is indicates uniform magnetic field. Now here imagine one north pole. That means I placed one north pole, not imagination. I kept one north pole here. If I place the north pole, what will happen? It will experience force in the direction of field. Why it is experiencing force in the direction of field? You observe carefully here. This what pole it is? North pole. Here what is there? South. North will attract towards south. Here what is there? North. North repulse. North repulse. So because of this north will go away. And because of south, it will attract. So this pole is experiencing force in the direction of magnetic field. Magnetic field is from where to where? Observe. Left to right. Force is from where to where? Left to right. Both are in same direction. So here, So north pole will experience force in the same direction of the field. Now let us discuss. Suppose I am taking one south pole now. South pole, this is south pole. In what direction will experience force? Obviously, south will attract towards north. South will attract towards north. And this south and south, they will repel, and south will attract towards north. So south attracts towards north means, so it is moving towards the north pole in this direction. So this is the force what we call here is F bar. This force we call it as F bar. This force is F bar. So what is the force formula we can write? The force formula is simply F bar is equal to M into B bar. Okay, F bar is equal to M into B bar. We have written, well done. Then what is our conclusion here? Conclusion means we have to write always when we are taking a south pole. For south pole, what is the situation for south pole? F bar and B bar are in same direction. F bar and B bar are in same direction. Same direction. When, sorry, south pole, what we have to write? See the diagram, not same direction. Same direction is wrong, because just now we wrote here. So let us check the diagram once. Here in the diagram, this is south pole. So south pole, this is the south pole. Here we have taken, this is south pole. Pole strength is M. So what happened to this one? It is attracted towards the north pole, because magnetic field lines, actually this north and south they don't mention. We have to imagine the north and south. How you will imagine, sir? Because we know that magnetic field lines are directed from where to where? North to south. Magnetic field lines are directed from north to south. So we have to imagine here there is north. Here we have to imagine there is south. But really we don't write anywhere here. Okay. Just we have to observe the south pole is experiencing force in opposite direction to the field, and north pole is experiencing same direction. North pole has been force in same direction of field. So here, what are our conclusions now? Our conclusions are, for south pole, F bar and B bar are in opposite directions. Opposite directions. And for north pole, what we have to say? North pole, F bar and B bar are in same direction. F bar and B bar are in same direction. These are our conclusions. For north pole placed in uniform antifield, south pole placed in uniform antifield. What the situation means is the situation. In the both the situation, force formula is F equal to MB. Magnitude of force is same, but directions are different. Directions are different. So here one direction of force for south pole and north pole are opposite. South pole means F bar and B bars are opposite direction. For north pole, F bar and B bar are same direction. That is given in this diagram. And some other important points we have to go through now. That is about when we are checking the field lines are crowded. Field lines are crowded. They are very closely to each other, very close to each other. One and other field lines are close. We call it as strong field. We call this field as strong. If the field lines are widen like that, so this is a weak field. So weak field and strong field. How to identify weak field and strong field? The field lines are closely packed. Closely packed here. It is called strong field. Here the field lines are wider to each other. It is called as weak field. Like that you have to analyze strong field and weak field. Strong field and weak field. I hope you are clear about what is strong field and what is weak field. These are the properties for the magnetic field lines. What we discussed in magnetic field lines, they are imaginary lines drawn in the path of unit north pole, which it is tends to move in the direction imagination. Next, what we take an isolated north pole and isolated south pole. Then we discussed about bar magnet, closed loops. Outside they are from north to south, inside from south to north. Closed loop they forms. And we discussed about the force experienced by the pole when placed in. South pole placed opposite to field, north pole placed same direction of field. It will experience force. That information we discussed. Then strong field and weak field, they are crowded. Strong field, they are wider. Weak field, straight and parallel. That is a uniform field, like that we discussed. Now the question is, there are two magnetic field lines. There are two magnetic field lines. Can they intersect like that? Can they intersect like that? So can the two magnetic field lines intersect? Means our answer is immediate answer no. Why no? So at the point of intersection, if you observe, we can draw the direction of magnetic field in two directions. Because here, suppose you observe here, for this to base is, south pole is there, north pole is there. Magnetic field lines are directed from where to where, north to south. Here I want to find magnetic field. I want to find magnetic field. There I am drawing one tangent. A tangent is drawn at that point. Wherever you want to, suppose I want to find magnetic field here, I am drawing one tangent. The tangent drawn at any point. Remember this one. The tangent drawn at any point to the field line, at any point to the field line will give the direction of magnetic field at that point. Direction of magnetic field at that point. So wherever, suppose at this point I consider for field line, I have drawn tangent. This is the magnetic field direction for this point. This is the magnetic field direction for this point. So like that, we have the magnetic field direction is given by tangent drawn to the field line. So here, if they intersect each other, at the point of intersection of two field lines, we can draw two tangents. So we are getting the magnetic field here as well as here. But actually magnetic field is what type of quantity? Means B bar is vector quantity. B bar is vector quantity. The vector quantity means it can't have two directions. It can't have two directions at a point. Two directions at a point. So two directions at a point we can't have, because the magnetic field induction is vector quantity. At same point it can't have two directions. So this situation is impossible. Impossible situation. What is impossible situation? So electric field lines intersecting is impossible situation. So our conclusion, no two field lines intersect. No two field lines intersect. So intersection is impossible. Why impossible? At the point of intersection of two field lines, we have drawn, this is one field line, this is one field line. For two field lines, they are intersecting at a point of intersection. For this field line, yellow line, you observe, yellow line, I have drawn one tangent like this. Blue line, other electric field line, for that I have drawn the tangent like that. If you observe the same point, we have two tangents we can draw. That means magnetic field can have two directions, which is impossible, because magnetic field is vector quantity. Vector quantity can't have two directions at a point. So we can say intersection of magnetic field lines is impossible, because no, that from that information I can conclude no two field lines intersect. No two field lines intersect each other. Intersect each other, we can conclude. Intersect each other. So this is the thing about field lines intersection. Very important application in electric field lines. So I hope you are clear with electric field lines topic. And this is a very important topic for objective point of view. Also, you need to have this complete thorough knowledge of field lines to discuss even some problems.